So this is one job I created. Okay. So this is the same job you have shared. So I was taking the values from this one actually.
You can go in the last run. Show me the last run. It shows succeeded now.
Oh, that's kind of a hard coding one. This is another job. I ran one job with hard coding the values actually without using the secure manager. So that time my all the jobs are getting succeeded. But when I use this one, it's throwing like error.
No, instead of doing this, you can go on the output error logs. Click on the error logs and watch it in the CloudWatch. Yeah, drag down. Drag it out a bit. The log streams you have now, come down. I have 2 log streams now. Just drag it down from the last event time. Drag it on right side. Okay, before last event right time now, we have a small pipe kind of separator now.
Oh yeah.
Yeah, drag it right. Yeah, open the below one. Open the below one. Second last one, open that. No, come down. Second last, do you have multiple arrows on the left hand side now? The second last one, you have to click open that. Just click here. And code exception in the threads also. Come down. No, not this one. Okay, go on top. Go on top. Take them top. More. You have to actually scroll it on top. Yeah, on the right hand corner, you have the option of display.
Yeah.
Click on view as plain text. Now press Ctrl F. A type error here, yes. Okay, click on next. Next. Just wait here, no? It's giving you line number. What it says. An error occurred, resource not found exception, gets value secret manager cannot find the specified. So you have to store the see, as the error says in the last, secret manager can't find the specified secret. That means the secret that you're trying to find in the secret manager, that is not there. Okay. Now go in your code. Go on to scripts. Okay, your secret name is Snowflake secret. Okay, yeah. Go on the secret manager. Okay, come down. No, go on secrets above.
Oh, sorry.
Hey, wait, man. Go on the glue script. Okay. Now come back to secret. It's Snowflake secret. Come here. Just Snowflake. The spellings are same.
Yeah, I just copied and pasted.
Okay, come down. Come down in the script. Wait. Service name is secret manager. Let me check my code. Region name. Man, your region name on line number 15 is wrong. See, you are creating your code in North Virginia. Your secret manager is in North Virginia, but you are mentioning AP South only. AP Southeast here.
This is this code only, right? Snowflake only, right? My Snowflake isn't for my API.
No, it has to be your AWS account. No, it is looking for the secret in the AWS service, not in the Snowflake service.
Oh, okay. So this should be from AWS.
Yeah. So if you go on the top of our top right hand corner, there's a North Virginia there, na? You found there. So you should say US-East-1.
Oh, okay.
Yeah, save this and run it. You are running it, no?
Yeah, it's running. Okay.
No, you have to go in error logs. I don't know which logs you are in. Go up.
Error logs.
No, you are at wrong place. Go back.
Yeah.
No, go up, go up. No, in the glue only,
Okay.
Somehow you are in monitoring. You go on ETL jobs. Open the job.
Job.
Just click on the job here. Just click on the job name. Your actual job name, first part. Click on that. Now come in runs. Go on error logs. Yeah, it says resource not found exception when calling at secret operation. Secret manager can't find a specified secret. Okay. Did you save the job before you run it?
Yeah, saved.
Okay. Go back to script. Come down. Snowflake secret name, passwords. Come down, secret ID, try secret name 2. Go up slightly. ठीक है. Can you do me a favor? Oh, wait. Go on the error logs. Let's check out the exact line number. Okay. Ideally, it should not happen now. that is fine. Open the box. Open the below one. Below one. You will never find anything in the upper one. Yeah, search for the error. There we have some genuine values. Yeah, press next. Okay. My secrets equal to get secret and 988. Can you send me the script?
Yeah, I'll send you.
And just one more time, show me the secret manager, okay? Okay, send me the script now.
I want to put in a file and send, right?
Yeah, you can send anything in the. You are sending it now?
Yeah.
Is it done?
Yeah, Shad, you didn't get it. Ashna long back.
I haven't got anything in the chat box. Yes. So here you have secret, so flag secret, yes, east one, secret name, password, region name, is correct. Then what is the secret name in your code?
Secret name password.
Can you show it to me? For sure it is no. There's no spelling mistake.
Yeah, let me check once.
Just show it to me for once. Because it mostly the issue is here only.
Yeah. Same as same will be.
Wait. No. You are doing it wrong now. This is the issue. See, the second one is a different secret. Okay. So what happens when you call the Snowflake secret? You get two things. It's like storing an ID and password, but for whom? So secret name says storing ID password for let's say Ritesh, Karthik. Okay, then his ID is this and his password is like this. Okay, this is what you are doing in your code.
Right.
Okay, if you see in my code, if I show it to you, okay, I will share my screen and then I explain you. I'll show you the differences between your code and my code. See, what you are trying to do here is, okay, in your code, you are thinking that this is a secret name password that you have to call. Okay, no, it is not like this. And then if you see my code, I am saying first of all I need Snowflake's URL. Okay, so what will happen when I try to get the secret name from the storage, this secret manager, I'll get a key value pair. Okay, I will get its ID and its value, both I'll get. If I show you the results of this get secret values response, okay, let me log into AWS. So if I go in AWS Glue, see, this is what I get. Okay, so when okay, not this one. Let me save view as plain text. So, okay, this is the complete thing that I get. Okay, when I call this service, when I call it like this now, okay, when I call this, when I get this response, okay, when I'm printing this response, this is the complete thing that I'm getting. Okay, but from this, what I'm needing, what I'm restricting it to in the block scenario. So if you see it here, I restrict this to, from the complete response, I restrict it to secret string. That means if I take it and paste it, or not so, if I convert this in JSON lint, if you see here, I am only interested in this part. Okay, but this also has two things: Snowflake's URL. It has, okay. It has only, I think you have created the secret in a wrong. So we have only one thing: Snowflake URL. This is the Snowflake URL, and this is the value of that URL. Okay.
No.
So what you have done while creating this secret manager, you have not created it perfectly. So you have, two options you have, like ID and then password. So
Right.
what I do, for me, it's only one thing: Snowflake URL. I take the URL from that answer and I, from the response, and I use it further. Then next, I have my different secret that is for my password. Okay. So I have two different ways I'm doing it. Okay.
So you're creating two
So
managers.
what I see, the way you have stored now, it will take a different approach. So what you have to do is, in your code, if it's possible for you, okay, what you have to do, no need to call it the secret name too. You have to comment this out, okay. Then just print the response here. Okay, just print the response here. From this response, you will get this something like this. You will get this secret string. You will have your first variable, and then you will have your second variable. So one by one, you have to pick the values of those. Using the dictionary methods of the Python. You can convert that into dictionary first. Okay, just learn it, convert the string to dictionary, just try that out, and get those values, and then use them.
Okay.
Okay. So I hope you got the answer that why it is failing. Because it's not able to find a secret. See, earlier it was your simpler thing, like you mistype the region. It was a different thing, but now it's due to the way of you are storing the passwords.
Yeah, same code with hard coding, right? I try executed. It runs fine actually.
Yeah, it is just with the secret manager only.
Okay, fine. Okay.
Okay, so let's move ahead.
And also, Jalaj, so this Python code, right? Instead of running the complete code, I can run like a Jupyter notebook also, right? One by one.
So you have to intelligently, paste this code into Jupyter, and then you can run it. See, one thing with the Jupyter notebook is, if let's say you paste this in one shell, okay, then you paste this in next shell, it will not identify. Because Python is an indentation based language now, so it all has to be in the same shell. And you can call it on different location that you can do. Yeah, so next topic is AWS Redshift. I should have it with me. Let's see. Redshift. Okay. So introduction is fairly easy. Now you guys know what is database and what is data warehouse. Redshift is another data warehouse competition to Snowflake. It is fully managed petabyte scale data warehouse. Okay. We can simply start with a few KBs also. It says gigabytes. This is I have copied from the official documentation. So we can actually copy. We can start with KBs or as low as possible. There's no restriction on the lower side, and we can go to petabyte scale data storage. Okay. So first thing, use cases are same for Redshift and Snowflake. There are no different use cases. Okay. It's just that which one you prefer. Okay. Now, only difference is architecture. In Snowflake, we guys had 3 layers. Storage were on S3. Then we had computation layer that was using EC2. In Snowflake console, we were calling it virtual warehouse. As per our requirement, as per our complexity, we were launching the virtual warehouse of our size, of our some configurations. Okay. And also we had this storage as storage and the compute capacity as a decoupled thing. Those things were not linked to each other. Okay. So we were free to enhance the space on the storage side without increasing the cost on the computing side, or we were able to enhance the size of compute machines without spending more money on the cost side. So that was possible on the Snowflake, but on Redshift it is not. Okay. So the Redshift that we have currently, that is Redshift structure, Redshift server 1. Okay, there you can go ahead and launch the Redshift servers. Okay, while you launch the server, we have to select the number of nodes. So if I come here, let's show it. Let's see it practically. It will be more easy to understand. So if I go on cluster and if I say create cluster, so Redshift is a data warehouse that works on cluster. Okay. So first of all, now you can compare this with Hadoop cluster or Spark cluster, where you have a master node and some worker node. That kind of cluster you can assume, but here there's no master or configure. It's just like multiple nodes will be there. Okay, your work will be in parallel. So let's see. When I come on the console, I have the option of choosing the cluster identifier. That means simply the name of cluster. Okay, something that you want to give as per your requirement and convenience. Then you select the node type. Node type basically means what level of machine you are looking for your workload. Okay, depends on your how much data you are going to store and how much complexity you have. Okay, so if you see one thing, okay, you have to be 200% cautious here that if you are trying to launch this Redshift server, do not create this server with RT 4x large node. This is the by default it comes here. I don't know why, but if you see the cost is $5,400 per month. Okay. If you calculate this in Indian rupees, it is almost 4 lakh or I mean more than 4.5 lakh rupees per month. So do not make this mistake. Come here, select DC2 large. Okay. For you guys, if your account is not more than 2 months old, for sure you will get some free trials as well. Choose a free trial. You will have the option of here. Okay. By default, you will see the option of free trial. Choose a free trial. If you cannot see that option, choose DC2 large node. Okay. And select the number of nodes as 1 only. This is more than enough, and you can see price has drastically come down. As we are not going to run this server for continuously for 1 month, we are not going to pay $229. Okay. Again repeating, if you have free option available, use that. If not, you can still run this server. This is going to cost you around $1 or $2 if you run it for 4 or 5 hours. Okay. So basically you can say, divide this number by 30. So you will get something around, what to say, something around, you will get a 7.5, or you can say almost $8 per day. And if you run it for 4 or 5 hours, you will just get $1 or $2 for your practice. Okay. Then if you want, you can load sample data. You can choose a username and password for yourself because it is a service. Okay. Like like a normal username and password, you can choose these things, username and generate a password. Then you can add some IAM roles for your clusters, and then some network settings. So coming back to PPT, Redshift is not like Snowflake. Okay, it is use case is same, work is same, but architecture is not same. So here what we have, when we launch or when we try to launch the server, we get this option of selecting the node types. And if you select the DC2 large node, what we get with this is you get 160 GB per node storage. Okay. So if I'm launching a single cluster, that means 160 GB of data max I can store. And I get 2 vCore CPUs with this thing. So here your compute and your storage are not different. Okay. So let's say I have one node of 160 GB and my compute capacity is fine, but I want let's say 40 GB more space in my cluster. Unfortunately, that is not possible. For that also, I have to come here. I'll have to come here and I'll have to say number of nodes as 2, and then my price will go up twice. Okay. Same thing is actually not happening on the Snowflake. You have the flexibility to choose the compute and storage as per your requirements separately. Now coming back. So see, when you launch this server, okay, when I launch this node 1, when I launch my server with a single node, okay, I am getting some compute capacity. That is my compute nodes. And with those compute nodes, I also get some storage capacity within my cluster, and this combination is actually called a Redshift server or provisioned architecture. Okay. Now, here, as I mentioned, your storage and compute are not decoupled. They come hand in hand, and if you want to increase the storage, you also have to pay for your compute capacity. If you increase your compute capacity, then you'll also have to pay for storage capacity, whether you use those things or not use them. Okay. So I'll stop here. If you have any questions.
Yeah, Jalis. So, like which one is better, Redshift or Snowflake?
See, there's no clear answer for that. Okay, it depends on multiple factors. I mean, uh, see, better if you say I'll move towards to Snowflake as per my personal choice. Okay, I am not saying this is the answer that you will find on the Google. As per my personal choice, I'll move towards the Snowflake. But some of the projects, they do not want to use multiple vendors. Let's say they are on. Let's say they choose AWS as a cloud. Okay, let's say during the migration they decide to choose AWS as their cloud, then they will prefer AWS services if it is there. Okay, so if AWS has a data warehouse, then they will choose that, and it is Redshift that they will choose. So Redshift is the answer in this case. They are not giving too much thinking about this. But there are some clients who are open to all the services as per their requirements. So they might choose Snowflake and they might choose Redshift. Again, depends on their requirement, what exact use case they have in hand. Okay. So and you have to answer it same way in your interviews as well. If someone asks you, do not say Redshift or do not say Snowflake. You can give your personal preferences that I might feel a Snowflake is better one in Redshift or Snowflake. But this is how you had to answer. Okay, it's not generic answer, it's a kind of specific answer. And sometimes like if the client choose Azure, they might stick to Synapse, they might not come to Redshift or Snowflake.
Okay.
Okay, so see, if you guys remember this from Spark, as I mentioned in the initially also, this compute actually works in the clustered. See, whenever you see this, whenever you hear this terminology, cluster, that basically means only one thing is going to happen. You will have a leader node or master node or whatever you call it. Okay, and then you will have worker nodes, slave nodes, or compute nodes, again whatever you call it. Okay, so and same sort of functionality you will have. You will submit your queries here. The queries will be received by leader node. Leader node will compile those queries, will generate a query plan for those, and it will share the query plan with all the compute nodes. And these compute nodes will also have the data allocated to them. Okay, and then these compute nodes will be working on their part of the data, processing the data, and sharing the results back to leader node. Responsibilities of leader node is again to collect back the results from the compute nodes and give it back to the user when it is done. Okay, so using this process, we are parallelizing the work. Okay, we will make the work parallelly running in it's like divide and conquer kind of approach again. And this is going to make your queries run faster on huge size of data. Now, one more interesting thing in Redshift is when you say number of nodes 1, okay, actually every node has some vCore capacities. Okay, that is you can see here. This one has 2 vCore CPUs. Okay, So this is more like going to have two slices. Okay, so in simple words, if I say Redshift compute nodes are further divided into number of slices. So if, as in depicted in this picture, if you have 4 compute nodes, you are going to start 8 parallel processes. Okay, not 4. We are going to start 8 parallel processes. Okay, so you can see these two blue squares are showing the this 2 slices of every compute node. So let's say you have a 1 GB of file. It's not going to be divided into 250 GB of 4 files. It's more or less going to be divided into 125 GB of 8 files. Okay. Now, and see, okay. Let's slightly move forward. Okay, then we'll come back to this image again. Redshift has some features. Okay, that is, first of all, it's, I mean, this is based on this feature. Based on these features, they try to promote themselves on the market. Massive parallel processing. Why they call it massive parallel processing? Because they say we are not only dividing the work on the compute level, we are also dividing the work on slice level. Okay, so that's why they call it massively parallel processing. Then they say columnar data storage. So this is something, every data warehouse does. Just you will not find any data warehouse that is on row level storage. Then third is data compression. Again, not so huge thing. Like whenever you store the data in data warehouses, more or less they are going to be stored in the compressed format. That is zipped format. The compression algorithm you can choose as per your requirement. Result caching, it is same in Snowflake as well. So if you run some query in Snowflake again and again, if you do not make any changes in the query, in that case the query will be cached. The result, the result will be cached, and next time when you execute the same query, it's going to be faster because it's not going to hit the S3 in that case. Our results are going to be saved on the top layer, and from the top layer results are going to serve to you again and again. So if I open the Snowflake architecture for just for the reference, see, so what happens when the first time you run the query, the data will be fetched from the storage layer, okay, and it will be served to you via cloud services layer, and the results will be cached in this cloud services layer for some time. Okay, let's say you run the query again one more time. In that case, you are not going to hit the storage layer again. You are simply going to serve your results from the cloud services layer. And if something that took 10 minutes on the first time, it might only take 1 or 2 minutes in the next time to be served to you. This is what caching does, and this is how caching works in every area of the this technologies. Okay, whether it is data warehouses, whether it is web services, whether it is databases. This is how caching works. The more frequent or the most latest results are always saved in cached layer, so they can be served if they are needed again immediately. So if I come back to this thing, and then we have description styles. So this is something you have to learn in Redshift. Okay, this is the only thing that kind of you have to understand in the Redshift. Okay, I mean, not only thing, it's like distribution styles, short keys, and few other things that we have to understand, like encoding. So what is distribution styles? So distribution styles in Redshifts are nothing but that how you store the data on your compute nodes. So now I'll come back on this architecture. Okay, so see, when we load the data on Redshift, so like we did on the Snowflake, we had this data in CSV files or some Parquet files. Okay, in the case of Redshift, you are going to find mostly the files being loaded from the S3 buckets. Okay, definitely it can be from other sources as well, but mostly it will be S3 buckets. Okay, so let's say we have a file of 1 GB and I run the copy command. Okay, in Snowflake we have copy command. Same way we have copy command on Redshift as well, that takes your data from source to your target table. Okay, only the syntax and the way of loading is bit different. That definitely we will see it practically. So say when we say the copy copy data from some location to a Snowflake table, sorry, to a Redshift table, my bad. How you are going to distribute the data on multiple compute nodes? Let's say we have a cluster where we have 4 compute nodes. Then how we are going to distribute the data? Okay, how that 1 GB is going to be distributed? That is decided based upon the distribution style you have chosen for that particular table. Okay. So let's say you choose even distribution style. It is very simple. Even basically means you have 4 compute nodes, 1 GB divided by 4, 250 MB of data on each node. It's going to distribute. As simple as that. Second is key distribution. Now, what's going to happen here? If from your data, you are going to select a column that is going to help you to distribute your data on all these nodes. Okay, so if I open my some example data, let's say we open sale report. Okay, not this one. Let's open something else. Let's say we open sale report, this one. Okay. So just suppose hypothetically that we have this data and we have to load this into Redshift. So from this data, okay, if you can choose a column that can do 2 things for you. First, it should divide the data equally between all the nodes or almost equally. Okay. That means when it divides data, it should be almost equal. By that I mean, let's do it practically. Okay, let's filter on data. Let's say we choose the column as color. I'll choose color. I'll choose aqua green. How many examples of aqua green we have? 5 examples. Okay, let's check with other thing. Let's say we choose blue. How many examples of blue we have? 782. So by looking at this data, I'll say color is not the column to choose to divide this data based on key distribution. Okay, then I might do the same analysis on all the columns and I might find out that column that divides my data somehow equally between all the compute nodes. That is the first requirement. And second thing is, and the most important one, you only choose the key distribution when you know that the queries that you're going to run in future are filtering, joining, or group buying. Somehow that column is, dominantly used in your queries. Okay, so let's say, let's just assume this color column is distributing your data almost equally on all the nodes. So what's going to happen? So what is going to happen? Your data for blue colors are going to be placed on compute node 1. Your data for red color are going to be placed on compute node 2. And likewise, all the data will be copied onto all the compute nodes like the same manner only. One thing it will make sure that if the data is, if the red color is on compute node 1, you will not find red colors examples on 2, 3, and 4. Okay. You might have multiple colors on compute node 1 like red, green, and white or yellow, but the same examples, again the same colors, red, green, white, yellow, will not be present on other nodes. So how this is actually going to help a developer or a user? So let's say in future, I write a query, select star from this table and do all these things and filter where color is red. Okay. In that case, what is going to happen? Let's say again, we are talking about the same 1 GB of file. And in that case, what's going to happen? This all compute nodes will have a kind of a metadata inform that red color is stored on compute node 1 and leader node is only going to talk to compute node 1. It's not going to scan compute node 2, 3, and 4. So if you are not scanning 75% of your capacity, that means obviously you are going to accelerate your query and it's going to run very much faster than the other queries. Okay, so if I summarize what I have said in the last 5 minutes, we choose key distribution only in the case when we know that if choosing particular column or list combination of columns can divide the data equally on all the compute nodes, and those columns are dominantly those columns are dominant in your SQL queries. Either they are used for joining the tables, or either they are used for filtering the tables, filtering the records, or they are used for group by the data or window functions like that. So I'll take a pause here. We have learned about two distribution styles, that is even and key. If you have any questions, let me know. Any questions?
No, Jalish.
Okay. So is it okay if I extend this by 10-15 minutes? Because we already started with 15 minutes late, so I think it should be okay.
Yeah, sure.
Yeah, no.
Okay. So see. Now third one is all distribution. Okay. All distribution basically what's going to do, it is going to create a copy of your data on all the compute nodes. So if you have 1 GB of file, in that case you will save 1 GB on compute node 1, 1 GB of compute node 2, 1 GB on 3, 1 GB on 4. So eventually you are saving 4 GB of data. Now, how it is helping you out? So it is first of all only advised for small data sets. Okay, it is only advised for small data sets. Those are oftenly used for your joins. If I say very technically, it is your dimension tables. Okay, if you have some knowledge of data modeling, fact tables, dimension tables, then it is your small dimension tables that you use very oftenly in your joins. In that case, for such tables, you should use or distribution style. In that case, how it is going to help you is, let's say we have a table, okay, that we distributed based on the key, let's say same color wala colors example. In that case, we have red colors on all the red colors example we have on compute node 1, and then let's say we join on the same color column, okay, let's say color code or something like that, and with the dimension table. So if we copy the dimension table on all the compute nodes, okay, in that case, the join will be performed on compute node 1 only. Okay, even for the join, we will not have to shuffle the data. Okay, so what I'm trying to say here is, let's say we have this example. Okay, let me try to explain this only. Let's say we have this example. Okay, I'll take it on here, and let's say instead of storing this color actual color names, we are storing 1. This is on node 1, and let's assume this is on node 2. And let's say we have some dimension table. Okay, let's say we have some dimension table. has only two columns, okay, color and color code, okay. And if I, if I do a even distribution on this table, okay, what's going to happen? My color code 1, red, 2, don't remember, but let's assume this is yellow, 3. Okay. So if I have this table in evenly distributed, so let's say what might happen, n1 gets this row. Okay, n1 gets this data. In that case, if I have to join, okay, in that case, if I have to join, what's going to happen? N1, one column, okay. Sorry, let's take this example also. Let's say on n2 we have this thing, and no, n3. Then let's take this example on. Let's take this example. What is going to happen? Let's say I say join. Okay. Now my node 1 has data for 2. Okay. My node 1 has data for 2. And let's assume this table is on evenly distributed. So it's 2 gets on node 3. So something we have on node 1, something we have on node 3, and we have to perform a join. In that case, a data shuffling will be required. Okay. Data will need to shuffle from node 3 to node 1, and this operation will take some time, and hence the join time will increase. And same way, if you see, the 3 option is actually available on node 2, and we have its data on node 1. Again, a shuffling operation will be required. But what if I completely copy this table and paste it on all the nodes? This is what your all distribution is. So in this case, 1 will be matched with 1, and all this 1 rows will be populated with a red. So in this case, a node data shuffling will be required. So see, we have n3 here, node 3 here, and we have n1 here. So all this 1 and 2 will be joined from the data of n1 only. Okay. Basically, what I'm trying to say, for all the keys, okay, for all the keys, for sure you will have the data on same node, and if you have the data on same node for the small dimension tables, we will not be requiring any data shuffling, and hence our queries will be faster. So I'll take a pause here. If you have any questions, please let me know, because this might be a bit confusing thing. And this is the most important thing in the Redshift. If you are saying that you know Redshift, this is something for sure they'll ask you in the interviews.
Chalish, can you please explain this again? I'm finding it difficult to understand.
Okay. Okay, let me think of some generic example, huh? Okay, assume it like, you have a lot of gifts. Okay, assume it like you have a lot of gifts, and those are stored in a sorted manner in multiple rooms. Okay, like room number 1, room number 2, room number 3, room number 4. Your task is you have to go in each room. Okay, and you have to apply some sticker on those gifts. So if your gift is wrapped up in a red color box, you have to apply a red sticker on that. Okay, this is your task. Now, obviously, gift size is going to be big and sticker size is going to be small. Correct? So if I store these two things like this, okay, room number 1 has the all red boxes, room number 2 has all the blue boxes, and room number 3 has all the yellow boxes. Okay. This is like your big table. You have distributed this based on the keys. Okay. Now, what is the dimension table in this case? It is just stickers. That is very small thing. Okay. So now if I store data evenly, some red stickers are stored on room number 1 and some are on room number 2 and some are on room number 3. And same goes for other two colors. Okay, in this case, what you'll have to do, let's see your 100 boxes. Okay, 33 stickers you found in the room number 1 and you applied there. Then you have to go in room number 2 and find the other 33 stickers and come back to room number 1 and attach those stickers back, to your red boxes. Then you have to go in room number 3, collect the red stickers from there and attach it back to your, come back to room number 1 and attach it to your gifts. This is normal way of doing it. But what if we simply, instead of evenly distributing the small things that we have in all the rooms, what if we have 100 stickers of every color in each of the room? Okay, then you will go in room number 1. You have 100 boxes of red color wrapped gift boxes. You will pick your 100 stickers and you will attach it in there. You will go in room number 2. You will find your blue boxes. You will take the blue stickers and you will attach it there only. Okay, this is, in this case, your stickers are kind of dimension table. They are small in sizes, hence they can be copied into each room. Okay. In contradictory example, if we have gift boxes and if let's say we have some big thing again, or we have something that we cannot fit in every room, stickers can be fit in every room. We can have multiple copies of the sticker. That is a doable thing. But something we have big that we cannot do, in that case, we have to arrange them, some different order. So we have to understand this in this complete scenario of all distribution. In this case, again talking technically, if you have small dimension table that you might use for joining purpose with multiple tables, so instead of asking your compiler to search the data on all the nodes, what you do, you copy the data on all the nodes, hence your compiler don't have to shuffle the data. That is all I'm trying to say here. Does it make some sense for you now?
Yeah.
100%, because this is important, because what these guys do, they are not going to directly ask you this question like what is all distribution. Okay, I mean sometimes they do, but not oftenly. What you will be asked, okay, so if you work on Redshift, then please explain me some way of arranging the data or some Redshift optimization techniques. This is how they are going to ask you, and this is one of the Redshift's optimization techniques that you use your options wisely. So you have the option of distributing the data, and if you use it wisely, you're optimizing it. Okay, Karthik, you are good.
Yeah, Jalaj.
Okay. See, now only one thing I'll say today. When you choose key distribution style, as I have mentioned, your data should get divided equally. Okay. So as we have seen the example in our file, okay, that for aqua green we just only had 5 rows, and for the blue we have 782 rows. So if same sort of example we have in the real time, we cannot use it. Why? Let's assume that we divide the data based on some cities in India. Okay, let's take two cities. Let's say Bangalore, and let's take some city, some two second tier cities. Okay, so in that case, data for Bangalore obviously going to be huge. It's going to be 40-50 million rows. In that case, your compute node 1 might not completely be able to store the data. Okay, so if you do that, either it will not store the data, it will fail, or let's say if it stores, it's storing 100% of your data. Okay, let's say compute node 1 is filled with all Bangalore's data, and then you have tier 2 city data on compute node T. Let's say on compute node 2, you are just have a few thousands of rows. That means you are only utilizing the 5% of your total capacity. Now let's assume you submit a query, and your leader nodes generates a query plan for that, and it submits the query plan to all these compute nodes 1 and 2. So obviously compute node 2 will be done in 30 seconds or 40 seconds. Let's assume that. Okay. And compute node 1, let's say, takes 50 minutes to complete the query. Okay. So something is completed in 30 seconds and something is completed in 15 minutes. And overall, you are going to get results in 15 minutes only. So instead of optimizing using the key distribution, you are de-optimizing it. Okay. So you have to make sure you are not creating such keys. You are not using such keys to divide your data. And this problem of having a huge data on single partition or single compute node and others are like kind of free only. This is called one hotkey issue. This can be there on Spark as well. This can be there on Redshift as well. This can be there on Hadoop as well. It can be there on everywhere you have partitioning. Okay. Or it can be there when you have parallel approach. So like Redshift, we have multiple compute nodes. That means we have parallel approach. So if we are making one node heavy and one very free, this is one hotkey problem. One hotkey basically means you have too much data for one key and you have almost nothing for other key. This is your one hotkey partition problem. How to solve it? Either you change the key or either you create the combination. That means you will come back to the same data, and instead of saying color only, you might say combination of design number and color if it works for you. Okay. You might use two different columns, or if it's not again, if it's not fitting, you might create a column of date and you might use color and date column. Okay. And you might give date priority to date. So I mean, it depends. It's these things come from experience, like which columns to use. But this is how it should be done. Again, do not worry. 99% of chances you are not going to choose the columns for this partitioning or this one hotkey because it is more functional problem. Okay, you might not know what these columns, like for this data set, we obviously the columns are very self-explanatory, but for technicals for your clients, it might not be to you guys. Okay, so this information you will receive it mostly from your leads. Okay, mostly from your data architects, business analysts. These are the guys who are going to tell you these things. But obviously for interviews, and obviously when they explain you that you have to use these two columns as a key columns for your table, you should know what they are trying to say. Okay, you should at least be in that position, like what they are trying to tell to me. You should not be completely blank at that point. Okay, so you might not be deciding this, but obviously you will be using these columns. Okay, so if you have any questions, you can let me know. Otherwise, we have a few more topics to cover in Redshift, like short keys, that's a spectrum, and a few more examples, a few more discussions about Redshift are pending. So let me know if you have any questions.
Jalaj, so basically, right, we have in a Snowflake also clustered by, which is nothing like a partition only, right?
Yes. So that is something I'm going to come back once I finish this Redshift. So Snowflake has micro partitioning and cluster by clustering. Two things are there: micro partitioning and clustering. Two things actually are pending from Snowflake side.
Also, one more doubt. So whether the Redshift and Snowflake both having update the columns like a normal RDBMS have?
You can. Yes, you can update the column. One thing. I'm sharing my screen now. Huh? If you see this option of Spark, okay. In this, I have this broadcast variables. Again, this broadcast variables is same thing. Use it for small data sets that needs to be shared across all the nodes to reduce the data transfer overhead. Okay, you can relate this to your all distributions, and here in Spark it is called broadcast variables. Explanation is actually exact same like this one. Use case explanation, its benefits are exactly same. And you might again have the same question in Spark. Please tell me some optimization techniques that you should have used or that you could use. Okay, so broadcast variable is one of the optimization techniques. See, in data engineering, one thing I'm telling you very generic, irrespective of the technology or the option that you use. If you transfer your data, if you shuffle your data, it's going to cost you. Okay. If you have clusters, one hotkey is going to cost you. If you have no backups, it's going to cost you. If you are treating your latest data and historical data in the same way, it's going to cost you. And this is generic. It's not like PySpark, it's not like Snowflake or Redshift, it's generic things. So if somebody is asking some question, you have to keep in mind data should not get shuffled, or if it is getting shuffled, it should be less only. I should have some backup, and I cannot treat my latest data with as same as my historical data. Historical data needs a different kind of approach, and latest data needs a different kind of approach. And if I have a cluster, I should make sure the cluster is working actually in parallel. It should not have that one part of cluster is doing all the work and another part of the cluster is doing nothing. Okay. So these are very generic concepts. Okay. These will help you in every technology actually. Okay. So if you have any questions, you can let me know. Otherwise, I'll wrap it up for the day.
No question.
Okay. Shurya, you are good. Something is said, but I didn't get it, but I'll take that as yes only. Okay, then guys, we'll meet tomorrow, same time. Thank you. Bye-bye.
Thank you all.